Okay, so good morning and welcome to our third meeting of Classical Mechanics 1 at CMI. Today is the 11th of August, Thursday, 2022. Yeah, so before we start, I had a question from Ritvik Bhattacharya, I think. So are you there? Can you hear me?
Yes, sir, I can.
Okay. Yeah, so the homeworks will be checked, marked, graded, and I will also discuss them in the class. And you will receive the corrected answer sheets in the coming days through Moodle. And if necessary, some comments will be made on the answer sheets itself. Does that answer your question?
Thank you, sir. And I wanted to point out that I am not Ritik Bhattacharya. I am Ryan.
Oh, okay. All right,
Sorry.
fine. I'm okay. The one name was highlighted, and I thought that person was speaking. I'm sorry about that. So this is Ryan Hota. Fine. Yeah. Are you at CMI or no? You are not at CMI. Fine. Okay. So let me just get started.
I'm sorry to interrupt again, sir, but I should say that I actually had to come to the clinic, medical clinic, for an emergency. Sir, I had to come to the medical clinic for an emergency. I might not be able to answer or attend for 10 minutes.
Okay. Fine. All right. Noted.
Thank you, sir.
Okay, so let us begin today's meeting of classical mechanics. So let me briefly go over some of the questions from the first problem set, which you have submitted through Moodle. Now, are there okay, perhaps not all questions need to be discussed here. Let me start by asking if there is anybody who would like me to mention anything about the first problem concerning the dependence of the torque on the origin of the coordinate frame.
Sir, I wanted to ask whether there needs to be one answer. Like, can there be multiple?
Yeah, if you feel there are multiple answers, I don't know if you're asking about this question or in general.
Yeah, in general also, but in particular to this question also.
Yeah. Okay. No, I mean, if you feel there is more than one answer, please, you're welcome to offer more than one answer. In this case, I think there is only one, essentially one answer. Here, we just are saying that, first of all, the torque is defined as R cross F, where F is the force and tau is the torque, R is the position vector. And we are changing the origin of the coordinate system. So initially we have a certain origin and particle is positioned here with position vector R, and there is some force acting on it. Yeah, and you've got its torque written over here. Now, suppose we switch to the new origin, to a new origin O prime. I will mark it over here. O prime, which is O plus A. So this is the vector A. And now the position vector is a new position vector, which I will denote R prime. Now, from this triangle, we can figure out that R is equal to A plus R prime. So that is the fundamental formula that we need to begin with, that to go from here to there, you could also go first right and then upwards. So based on this, we put this and in the formula. Now, the torque with respect to the new origin, by definition, is R prime cross the force acting on the particle. and we want to relate it to the torque with respect to the old origin. So we simply re-express r prime in terms of r. For that, we write r prime as r minus a, and then cross to the f. So this is r cross f minus a cross f. So I would say that tau prime is equal to tau minus a cross f. So this is the expected answer. Any question concerning this?
Sir, again, a vector is like oddest vector minus o vector, right? Because we want to relate the two origins.
Correct. Yeah. Okay, so let me address your question. So suppose the position vector of the origin O is actually the zero vector. That is this zero vector. And then I add to that zero vector the A vector and arrive at the new origin O prime. That is what the formula O prime equal to O plus A is meant to convey. Yeah, I think your question is well taken. Perhaps this formula was a little mysterious, but this is what is meant. If you wish, you can think of some even more primitive origin sitting somewhere else, O double prime, and then there is some vector for which O is the, pointing towards O, and then there's an A from there to O prime. And then we would say that, then this would correspond to this formula. Is that okay?
Yes, sir. Sir, I wanted to ask that whether if we like replace a vector by oddest vector minus o, like will it be fine?
Yeah, sure. Oh, you're saying that if you rewrite A as O prime minus O. Okay, fine. You are proposing that and putting
Yes,
it in this formula. Yeah, that is acceptable. Yes, that is acceptable. Yeah.
Okay.
Was that Nirjar? Please tell me who you are.
Yes, sir. I'm Nirjar.
Nirjar Nath. Yeah, and I believe you are at CMI. Am I right?
Yes, sir. I'm.
Okay, very good. Yeah, I have been kindly assisted by Onkon Mukherjee, who has given me a list of students who are at CMI. So that is why I know you're here. Okay, let me now go to the second problem. Yes, please.
So I think we all had a question. So for none of these questions, do we have to prove that a vector product is actually distributive, or we have to go via the additive inverse way to add it and to add vectors and to subtract vectors? We can always assume these axioms work, right? Or do we have to actually prove?
No, we are not expecting, I do not expect you to prove those axioms, not axioms, prove those properties. In fact, it's okay. Perhaps I was not very careful last time, but no, short answer is no, you are not expected to prove them. You can assume distributivity and proceed. Since we said you can scale a vector by a real number, that real number could be negative, and we also have the property of addition already in our hands. So then you have subtraction coming straight away by combining addition and scaling by negative numbers. So you are not expected to. You can assume those properties. Is that okay?
Yes, sir. Thank you so much.
Okay, that was Somendra Singh. Is that right?
Yes, sir.
Okay, Carola, fine. Let me, and as far as I know, you are not at CMI. Okay, so let me proceed to the second question, which concerns a particle moving on a circle. Now, here I did not say that the particle is moving clockwise or counterclockwise. For that matter, since I said nothing, the particle could be moving sometimes clockwise, retracing its path and doing a funny dance. But let us focus on a certain situation and then answer the question and then address the question: what happens if the direction is reversed? So to make things clear, what you are expected to do is to first assume that the motion is in some manner. So let us suppose counterclockwise. motion. Yeah, I mean, we have not said it. We have not even said that the motion is uniform, right? So the particle could be speeding up, slowing down, coming to rest. All sorts of things could happen. But let us address. Suppose the particle is moving counterclockwise. In other words, in this direction, and we are told that the origin is at the center of the circle. Now the velocity of the particle therefore points in this manner, and this is the position vector r. So then r cross v points in this case out of the plane of the paper. Yeah, out of the plane of the paper. So L is equal to mr cross v out of the plane. And this is true no matter where the particle is. The same direction of L is obtained. So that is now, of course, if particle moves clockwise, L is reversed in direction. Okay, so this is what was expected, and I think many of you have. Yeah.
Sir, I have like without loss of generality assumed that the particle moves counterclockwise. So like, should I mention that L is reversed in direction? I just wrote at the end that a similar argument follows for like if the particle moves clockwise.
Yeah, it's all. Yeah, I'm happy you have said a similar. Okay, let me say two things. One, I am happy that you have said that there is another option, which is the opposite directed motion, and I'm happy that you have said that a similar argument applies. However, to finish that argument, you have to tell what the result is. After doing the argument, what is the result? The result is very simple. Simply, L is reversed in direction. So I want you to say that. If you don't say that, I'm afraid your answer is not complete. Yeah, so yeah.
Yes, sir,
All right. Okay. All right, Najjar. Yes. Any other question about this part 2A? If not, we will go to part B. Part B is slightly different, where we have changed our origin to be located outside the disk defined by the circle. So the origin could be somewhere here, and then yeah. So many of you have looked at this carefully and arrived at the right answer. So I'm very glad. So the summary is that again we will assume a counter clockwise motion. In other words, motion directed this way. Now the answer actually depends on which arc of the circle the particle is instantaneously located at, and in the different cases the direction of L is changed. So in this case, if the particle is in the near arc or the minor arc, so this is the near arc or the minor arc, that is the one near the origin, then the R, which is pointing this way, and V is pointing this way, R cross V points into the plane of the paper. Yeah. On the other hand, if you're at this far arc, then R is this way and V is this way. R cross V points out of the plane of the paper. Right? So there is this important difference. And there are two exceptional cases, which is when the particle.
Yeah, that will be, and in this case, L is 0.
Indeed. So in the two exceptional cases where okay, so if P is the particle's location, yeah, and if OP is tangent to the circle, then L is simply 0, and therefore points in any direction. It has no well-defined direction. You can say it points in all directions. So this is the situation here. And if and as before, if direction of motion is reversed, anywhere. I mean, it could be locally reversed. I'm not saying it's reversed entirely all over the circle, but if it's reversed in any segment of the circle, any arc of the circle, then the direction of L is reversed. Yeah, and that comes just from the original formula itself. If we reverse the sign, L reverse the sign. Okay, so that is part B. This is what you are expected to do. Yeah, I hope you have drawn figures and understood these three possibilities. Okay, any question? Okay, if not, let us proceed to the third problem. Here we are told that there are two vectors, omega and r. Of course, omega is supposed to remind you of a angular velocity. Yeah, remind or in anticipation of the use of omega for an angular velocity, and r is the position of a particle, for instance. And then you are simply asked to write omega cross r, its magnitude squared in terms of dot products. So, I mean, you are explicitly asked to write it in terms of dot products. The answer is fairly straightforward. So I won't go through it. I will simply tell you that the answer is omega dot omega times r dot r minus omega dot r whole squared. Okay, so yeah, this is a useful expression. Of course, it's coming because you have the cross product gives you a sine squared, and you rewrite the sine squared as 1 minus cosine squared, and then the cosine squared gives you this dot product, and the ones give you the magnitudes, squares of magnitudes. Yeah, so that is relatively straightforward, I think, and I think most of you have got it. Any question concerning that? Okay. The fourth problem, by the way, this quantity comes up in various places in physics, and you will come across it, for instance, in rigid body motion and elsewhere. Or just when one looks at motion relative to a rotating frame, this kind of expression comes up frequently. Okay, then in problem 4, we consider a particle that is subject to a force of the form v cross h, where h is some vector and v is the velocity of the particle. And we are asked to determine or comment on the work done by the work done by the force in displacing the particle infinitesimally. And I think most of you have figured out that the answer is that the infinitesimal work done is 0, and that is because dw is equal to f dot ds. Yeah, and that is v cross h dotted with ds, and you have to make the observation that v and ds are collinear. Yeah, they point along the same direction. So, I mean, a picture would also help perhaps. You have a particle located here. Its instantaneous velocity is pointing this way. So the displacement it suffers in a small instant of time points in the same direction. And therefore, the parallel pipette defined by these three vectors has a 0 volume. Yeah, so this quantity is simply 0. And so the infinitesimal work done is 0, and if you move to the next, and this is true anywhere along the trajectory. So such forces do no work, and such forces are important in physics. There are several examples. There are some important examples we'll come across. Does anybody want to offer an example of such a force?
The magnetic force is such an example.
Yes, indeed. May I know who spoke?
Sir, Mayur and Shastri.
Mayur and Shastri, is it? Okay. Okay, very good. Yeah. So yeah. So the magnetic Lorentz force. In that case, this H vector is actually the magnetic field times the charge of the particle. Okay, so it has that interpretation. There are other forces also like this.
So even the centripetal force, perhaps.
Can you revise that? You are very close, but not quite right. You meant to say the Coriolis force. Yeah, also has this property. It does no work. Okay, so who offered centripetal?
Yes, sir. Yes, sir. Centripetal force, sir.
Okay, that was Somendra Singh?
Yes, sir.
Yeah. So I hope you got my response to that. Yeah, so the centripetal force points towards the center of a circle.
Yes, sir.
So that direction is different from the direction of the motion of the particle, which is tangent to the circle. So in that case, the angle is not zero. So that centripetal force can do work.
But sir, the instantaneous velocity is always perpendicular to the force, right?
Yeah. Okay, perhaps I misunderstood you. I'm sorry. You are asking whether. Okay. I'm very sorry. I'm sorry. I was asking a slightly different question. You have answered a different question. I was asking for forces that have this form, V cross H form.
Okay, sorry.
And you have answered a different question, which I misunderstood and misspoke. You are quite right that a centripetal force doesn't do work. Yeah, and that is for a different reason, and that is simply because the force is directed towards the center and the motion is tangential, and therefore F dot ds is zero. You're quite right, but it's not that the centripetal force itself. Okay, we will see. Yeah. Okay. Yeah, so okay, perhaps I should withdraw my statement. You are right on all counts. So yeah, give me a moment. Any other questions concerning this?
So the Coriolis force is a pseudo force that acts when you're looking at things from a rotating reference frame, right?
Indeed. Yeah. So so that is what you said is correct. It is one of the forces, one of the fictitious forces, one that is felt when a particle's motion is referred to a rotating frame of reference. Yeah. So I mean, we will talk about these things at a later stage. Yeah. Let us. And that later stage maybe after 2 minutes or something. But we will talk more about these things. Right now, we don't have the background to really talk about Coriolis and centripetal forces in detail. So excuse me for that. Now, let's. But any other question concerning the problem itself?
Could you please tell me why the angular velocity vector points up vertically upwards? Like, okay, I know that it points because of the cross product rule, but why? Like, if
okay, yeah. So, all right. See, right now I have not, in any careful way, defined the angular velocity vector. We are simply considering some vector omega and given it a direction. So your question is not answered in this context. But yeah, it is. I mean, it's a matter of what is convenient and useful. If you have a body that is rotating, at least over a short instant of time, a short duration of time, one can define an axis of rotation. This is a fundamental fact going back to an observation of Euler, that an infinitesimal rotation is always a rotation about some axis. And now, of course, how fast it is rotating about that axis will give you a certain magnitude. So if you combine these two features, namely the existence of an axis, and for that axis, you will choose a unit vector in the direction of that axis, and a magnitude given by the rate of rotation. Combining these two features, it is possible to define a vector that points along the instantaneous axis of rotation. and we name that vector the angular velocity vector. Does that provide some background?
Yes,
Okay.
that provides.
Yeah, who was
We
that?
will be covering that in this course, right?
Yeah, not now. We will talk about that later on. If we can discuss some things about rigid bodies and rotation of such objects, then it will naturally come up over there. Yeah. Sorry, who was that?
I'm Anhad.
No, please repeat your name. I didn't.
Anhad, ANHAD.
Anhad, yes. Okay. Anhad Chaturvedi. Okay. Fine. Now let us. Oh, what happened? Yeah. So we will talk about things like Coriolis forces, etc. later on. Now, at present, I want to speak about problem 5 briefly, where we consider a particle that is moving on a sphere. Yeah, and the origin is at the center of the sphere. The position vector of the particle is r. Now, the nature, and then we are told that the particle is subject to a force. Okay, I just said that this is a vector, so but let me call it f for convenience. Yeah, it is defined as minus omega cross r. Okay, so this is our vector. I claim that in future studies we will come to learn that this vector is the centrifugal force per unit mass. Okay, so yeah, so the quantity I defined in problem 5 has a physical meaning. It is the centrifugal force felt by a particle when referred to a rotating frame. It has this expression, so it is a important quantity from that viewpoint. And that also relates to the questions in part 4. Somebody talked about centripetal force. If by that you mean the oppositely directed version of this, then you are this is related to that. Okay, so now of course, being a good name, the name should give the answer already. Yeah, so let us finish this figure. Omega is the angular velocity. It points in the direction of the axis of rotation of this sphere. And being from the name centrifugal, it means the opposite of centripetal, and it therefore points away from the axis. Yeah, so the I will explain the answer, of course, but I want to state the answer first. So the answer is that this force F points radially outward in the plane defined by the latitude through r. Okay, so that is a nice way to state the answer. Many of you have stated the answer in other ways. So let us just, so the claim is that this force simply points this way. It is radially outward in the plane defined by the latitude through the point r. Okay, so the point r, okay, Shubham Mal says, I did this algebraically, didn't understand the figure. Okay, well, I hope you will understand the figure here. I will look at your algebraic answer on Moodle. So the point is, a point on this sphere is on some latitude. So that latitude, except if it is at the poles, defines a circle. That the circle lies on a certain plane, and I claim that this vector points radially outwards from there. Now, it's important to have in mind that this vector points from the position of the particle. I mean, it would not be right to say that the vector points from the equator or something like that. Yeah. So it really emanates from the position of the particle. So we would like to have that viewpoint. And furthermore, if you want to take some physical intuition, this centrifugal force is a kind of force that one feels when you are on a merry-go-round spinning, and that force tends to throw you out of that merry-go-round. So it is possible to feel it. You feel it. It's not that somebody somewhere else feels it. Yeah. So that's why I want to say that this vector is emanating from the point at which the particle is located. So is the statement or the answer clear? I have not yet derived the answer, but is the statement or the answer clear?
Yes, sir. Sir, it is clear, but I mean, like, I have done it the other way. Like, I have defined the direction of that thing to be another.
Sure. Yeah.
It is fine.
Yeah. I'm fine with your having stated the answer in other ways. Yeah, that is fine. And
so this vector emanating from the particle,
yeah.
sir, how is this? How can we derive this from the formula?
No, you don't derive this from this formula. You get that intuition from my voice and from your experience. Yeah. So no, I am serious here. Not everything can be derived from this little formula I have given. There are missing pieces here. So I am adding those missing pieces. Yeah. So yeah. So whether you like it or not, some of the things we present do not have all the pieces of the puzzle there. This one is not there. So that's why I am mentioning it to you now. Yeah, but okay, so please excuse me. It is if I had to be axiomatically correct, I would have had to say a lot more. But if I were to do that, this course will not proceed anywhere. So I have been a bit terse. So that was that Saurabh Dey?
Yes, sir.
Yeah. So yeah, I'm sorry to disappoint you. Yes, the problem is not stated in a fully complete manner. This is an accepted shortcoming of mine. However, I am trying to reduce that shortcoming by adding a few insights over here.
Thank you, sir.
Yeah, and this this formula has some physical significance. That's also something I'm trying to convey to you. It is not some cooked up expression that we just write for problem 5.
Sir, I've represented, so when I was submitting the homework, I represented the thing in terms of r parallel to the axis and r perpendicular, and wrote everything in terms of that.
Okay.
Will that be fine?
Yeah, we will have a look at it. As long as it is stated clearly, it should be okay. Yeah.
Sir, I misunderstood this problem. I thought that the circle, like the origin was in the center of the circle.
But I thought we were told that the origin.
Yeah, I think I just okay. Only reasoning that I misinterpreted this problem.
Okay, yeah. So that is Suchir Kaustav, I think. Yeah. So you have taken the origin at the center of this latitude circle. I mean, that is okay. But then, given that the origin has been mentioned to be at the center of the sphere, you would have to transform
the problem. Basically, that's taken of a sphere at a circle, and that's
okay, fine. All right. I understand your confusion. Fine. Okay. Anyway, we live and we learn. So let me then just finish this story very briefly. This vector, let us start with the basic things. First of all, the cross product is perpendicular to both vectors. Yeah, so in particular, f is perpendicular to omega. Okay, so this is a first fact, and therefore since f must be perpendicular to omega, so this implies that f must lie in the latitude plane. So that is one basic conclusion we can draw. And furthermore, f must be perpendicular to omega cross r as well, because that's the other vector in this cross product. Yeah, so now the question is, so a vector that's perpendicular to omega cross r must necessarily lie in the plane spanned by omega and r. Okay, so let me state that. This implies that f must lie in the plane spanned by omega and r. Okay, I hope you can digest that. Let us think for a moment. Yeah, omega cross r is perpendicular to both omega and r. And if you have a vector is perpendicular to that itself, it must necessarily lie in the plane spanned by omega and r. That's all I'm saying. Yeah, so I invite you to take a moment to think about that. But any questions? Okay. Now this plane spanned by omega and r has a geometric or geographical significance. Which plane is this? Please give it a name.
Longitude.
Indeed, yeah. So this is the plane of the longitude through r. Yeah. So combining these two results, 1 and 2, we conclude that the vector f f must point in along the intersection of the latitude and longitude planes. Intersection of latitude and longitude planes. And that is very easy to visualize. You got the latitude plane, you got the longitude plane, and they would cut each other. And that I hope will explain to you why it has to point either radially outward or radially inward at that point. Okay. Of course, arguing this way naturally makes the base point of this vector lie at the point. Yeah, I mean, even if you knew nothing about rotating on a merry-go-round and so on, it is very natural to consider this vector to have to emanate from this point based on the kind of argument we are currently making. So that is, I hope Saurav is willing to take a little bit of that insight. Okay, what is, so Shyam Patankar asks, what is meant by the plane of the longitude through R? Okay, the longitude through R is, okay, I mean, if you call this the North Pole and this the South Pole, then there is a great circle passing through NS and the point at which the particle is located. I give the name longitude to that great circle, and then that great circle defines a plane. Is that okay, Shyam Patankar?
Yes, thank you.
Okay, great. All right, so now we are almost done. We have identified the direction of this vector up to 2 possibilities, namely radially inward or outward. Now that can be also determined, and I will let me do that very quickly here. Let's go using the thumb rule. Yeah, the right hand thumb rule. The first stage is to take omega cross r. So omega is upwards. Omega is upwards cross r. You will get a vector that points tangential to the sphere and lying in the longitude, latitude plane. Okay, so omega cross r is tangent to sphere and pointing counterclockwise. Omega cross r points into the plane over here. Then I take omega itself and displace it to this point, omega, and then I've got omega cross r, which is into the plane at that point. And if I take that cross product, omega cross r, it will point radially inwards. Okay, so I hope you are able to follow. So omega cross r would point this way. Are you with me so far?
Yes.
Okay, thank you. And finally, we put a minus sign and reverse the orientation. So we go radially outward. So that's the story. We have determined that the centrifugal force, as the name might suggest, points radially outwards on the latitude plane. I would like to emphasize that along with your algebraic or other differential calculations, it is very important to know how to state the answer. And it is for that reason I have written the answer in words. It's an extremely useful skill to be able to present your answer in a manner that your audience can understand and doesn't go to sleep. So that's why we introduce these things like latitude, longitude, and geography, and so on. Some students came and asked me, how do you write the answer? So that is why I've done it this way.
Sir,
yes, please.
Sir, geometrically, I have got that the direction of the given vector is along the vertical projection of r vector on the plane that is perpendicular to the axis of rotation, and it passes through the center of the circle. So it's basically the same thing. Since you could display this vector in the sphere, it is basically the same thing.
Yeah, I heard you, and yeah, what you said sounds right. Yeah, yes, Nirja. Yeah, so yeah, you are not obliged to use geographic terminology. You can use other terms like orthogonal projections. I'm happy with that.
Sir, in this type of motion, the omega vector should start from the origin of the sphere or the center of the circle in which the particle rotates?
Normally, we would see the omega vector in this case. See, we are doing fancy things by elementary means. All right. So yeah, so we are free to parallel translate vectors as we find convenient. So I would say that to begin with, it is most convenient to think of omega as a vector emanating from the center of the sphere. Yeah. However, in certain circumstances, like we just now talked about, it may be convenient to parallel translate it to the location, instantaneous location of the particle. So that's what I've done. I do not see very much use of moving it to the center of this circle. It's also fine. I mean, yeah, if you find it helpful, you may do so. I would like to just point out one thing, and this is based on a question I received by email. The nature of the motion of the particle, does it matter in answering this question?
I think it's no, because it's instantaneous, right? At that point, you actually don't know what's happening at that particular point.
There is no time aspect in the question at all. So
Correct. So you both have said relevant things. The nature of motion, by that I mean, what is the trajectory like? Is the particle moving on a circle? Is the particle moving on a latitude circle? Is the particle moving towards Greenland or towards India? All these questions are not relevant to this problem, because the force or this vector we are considering does not depend on velocities at all. It depends only on the instantaneous location of the particle, and of course on the omega vector, which is some other fixed thing. So for that reason, the nature of motion, by that I mean the velocity, for instance, does not enter this story at all. So you don't need to worry yourself about whether the particle is moving on this circle. Yeah, I think that some of you made that assumption. There is no need for that. of course, if the particle was moving on this circle, then it may make sense to keep this omega vector emanating from the center of that circle. All right. So those circumstances, it is helpful to do that. But you do what is helpful in your problem. Okay. Any further question about this?
Yes, sir. So my question is that if you were to do this algebraically, you will end up getting an answer that it exists in the XZ plane, because you can actually parallel translate all these vectors back to the XZ plane, right? Because they are all in space. So you can actually put them back on the XZ plane, and the XZ plane is actually perpendicular to both omega and omega cross R. However, when you do that, I didn't actually understand any physical, I didn't have any physical intuition of the problem at all. So how would you actually address that? Because I didn't know that these are forces that, and this is actually a centrifugal force or something like that. So I only had mathematical tools at my disposal. Yes. And I could only use that. And I neither did I have any idea about the longitudinal aspect and the latitudinal coordinates of which you described right now. So how does one learn those things as well?
Okay, you have articulated your question in a very, very nice way. May I know your name?
Name is Somendra, sir.
Somendra Singh. Yeah. Yes. So how do you learn these things? You have already learned, and the way is to be present in the class on time. That's the long and short of it. And to have thought about it so that you know what you know and what you don't know. Okay, but I will have to look at your answer sheet to understand precisely what you have done. I don't see why this vector lies in the XZ plane. If Z points upwards, as far as I understand, this points in a plane parallel to the XY plane.
No, sir. I have assumed that the upward direction is actually the J direction.
Oh, okay, fine. All right, okay. Then you are fine. Just a moment. I have somebody at the door. Okay, so Somendra, yeah, I'm sorry. At the odd occasion of somebody knocking on the door, and when I open it, the person has vanished. So please bring me back to your question. Have I addressed your question?
Yes, sir. So just one statement, sir. So can we consider this to be one of those examples, probably trivial, where mathematics really can't capture all nuances of physical intuition, or can mathematics actually capture all physical nuances completely?
See, look, if I state my problem in a manner, translate all the physics into very precise mathematics, then presumably having faith in mathematics will take care of it. The problem lies here in an incomplete specification of the problem, or a less than complete statement of the procedures you're allowed to follow. Yeah, so that is the issue. But this is an essential problem. One has to understand that nature and physics are much bigger than mathematical schemes that we can set up. There are often issues that we cannot state because we've not even thought about them, or we've not looked at them carefully enough. And it would be a pointless exercise to try to mention everything. Then there will be no end to it. So the message is that it is really in practice a combination of some physical intuition and mathematical skill and logical sensibility that is needed. Yeah.
Thank you, sir. Thank you very much.
Okay, sure. Yeah. Let me say also that I did not mention that this is the centrifugal force. You see, I did not mention it. So no wonder you did not know about it. It's okay. You now learned about it 2 days later. I think that is good going. At least you learned the name. And if you go look up in some Latin dictionary, you will discover that centripetal means centri is center, and petal is towards, so it's towards the center, and centrifugal is the opposite direction. So using those words, you can get a lot of quick information. Yeah, but that is no substitute for being actually able to use the right hand thumb rule and get the answer. I don't feel that that is so difficult. You don't need a whole lot of mathematical knowledge to just rotate your fingers and get this answer.
Sir, I had a few basic questions. Could I ask?
Okay.
Sorry,
who is speaking? Sorry, who is speaking?
If I
Ryan Hota, fine. I mean, do they concern this problem or this problem set?
Yes, they do concern a thing you just said.
Okay, fine. Yeah.
How do I determine whether a force is centripetal or not? Like given a force, there is.
No. See, it depends on the context. Suppose we are talking about motion on a circle or something, then it makes sense to ask whether the force you are talking about is centripetal. In a very general context, it is not very meaningful. Yeah, so it really needs some additional context. Yeah. So I mean, there may be a particle moving on a circular hoop or something, and there may be many forces acting on it, one of which is some frictional force, and there may be a charged particle also, maybe feeling some electric force, but there may also be a little string that is tied to the particle attached to the center and being whirled around. And there may be some centripetal thing as well, or some centrifugal thing. So yeah, but the name, it gives it away. You would want to call a force centripetal if it points towards some appropriate center. Now, if there is some appropriate center in your problem, if the problem is that a particle is not moving on a circle but on some arc, that arc, at least locally, may still be approximated by some arc of a circle, and then that circle may have a radius of curvature and a center that can be instantaneously defined. And then, okay, then if your force points towards that center, you might still want to call it centripetal. So it's a matter of useful terminology. Yeah. Is that okay?
Thank you, sir. Yeah.
Yeah. So I want to clarify one thing. I am not saying that you should have known that this force is called centrifugal and therefore known its direction. No. I am saying, having done the problem, I want to give a name for the answer. That's all I am doing. I am just giving a name for the answer that you have painstakingly obtained, so that in future you will have a quick, ready reference way of remembering the answer. That's all. There is no substitute for actually rotating your fingers or multiplying vectors or doing your geometry. Okay, so now that we have spent the better part of 52 minutes, is it, on problem set 1, let us go back to our discussion from last time. Yeah. Okay. So last time we spoke about linear independence, which I don't want to go over again, but we will illustrate through examples. I want to introduce terms which many of you are already familiar with. So we will talk about what we call Cartesian axes, named after René Descartes, as any choice of mutually perpendicular axes x, y, z in three-dimensional Euclidean space. So this is an example of that, x, y, and z. And the coordinate axes themselves extend indefinitely, both forward and backward. Yeah. Now we will call a Cartesian orthonormal frame the following construct. So we denote the unit vectors along the Cartesian axis by x hat, y hat, and z hat. Some people use I hat, j hat, k hat. I will by and large avoid that. Now they are orthonormal in the sense that they each have unit norm. That is what normal means. Ortho means perpendicular. So unit norm, and that is conveyed through this set of equalities. So the length of the x hat vector x dot x square, I mean, that's a square of the length, is 1, and so also for y dot y and z dot z. So that is unit norm condition, and then orthogonality is encapsulated in these equalities. X dot y is 0, y dot z is 0, and z dot x is 0, all hatted things. So an orthonormal frame, a Cartesian orthonormal frame, would be 3 such unit vectors satisfying these conditions. Now, given such a frame, we can ask whether it is right-handed or left-handed. All right, so this is an additional stipulation. Both possibilities exist. So we will say that a frame, a Cartesian or an orthonormal frame, is right-handed if the following condition holds, namely x cross y is equal to z. Okay, x hat cross y hat is equal to z hat. So I must say that this is an ordered basis. It's a very important issue. When we talk about bases, we have to be clear whether it's an ordered basis or not. So in this case, it's ordered. X is coming first, y, and then z. And then what this is saying, if the cross product of the first two vectors is the third, then we will call that frame right-handed. And if it is minus the third, we will call it left-handed. Yeah, so I mean, let me draw a figure to clarify this. X and y are orthogonal, so I can just, without loss of generality, draw them perpendicular to each other on some plane. Now, if z must be perpendicular to both these and be a unit vector, there are two possibilities. One is this way and one is that way. So the choice where z goes upwards is called right-handed, and the choice where z goes downwards is called left-handed. If this was chosen to be said, then that would be a left-handed system. So in this discussion, we will work with right-handed frames. So when I say a frame, if I don't say it's right-handed, we shall have to assume that that's the case. Okay, so this picture repeats the same thing. So this is a left-handed frame, because if I take the cross product x cross y, the cross product x cross y points leftward, whereas my z-axis has been chosen rightward. So this is a left-handed system. Okay. Any question about that? So now x hat, y hat, and z hat form a basis for R3. And I'm introducing this word for the first time. Is basis in the sense that they are linearly independent in the first instance. And moreover, any vector in this three-dimensional space can be written uniquely as a linear combination of the three. So any vector A can be written as a linear combination ax x hat plus ay y hat plus az z hat. Okay. So basis would be a set of linearly independent vectors such that any vector can be uniquely decomposed as a linear combination. The details of this will be discussed in your linear algebra course, or you may already know it. Okay, so now the three real numbers ax, ay, and az are called the components of A along the three coordinate frame vectors. I mean, I've already introduced the term component, so it's only to be checked. We had already defined the component of A in the direction of x hat as A dot x hat. So if you take the dot product here with x hat and use orthogonality, A dot x hat, you will notice you will get ax x hat dot x hat, which is 1. Yeah, plus the other two terms vanish because ay times y hat dot x hat is simply 0. And say also az z hat dot x hat is also 0 by orthogonality. So we have verified that ax, ay, and az are precisely the components of the vector A along the three coordinate frame vectors. And just to complete that terminology, we also notice that AX X hat, that is the first summand here, is actually the projection, orthogonal projection of A in the direction of X. Yeah, this is again a concept we had introduced previously. It's the orthogonal projection of A along X. And many of you have freely used such concepts even in problem 5. Okay. And we say in words that the vector A has been resolved into its components and written as a sum of its orthogonal projections along the orthonormal basis vectors. So that's a mouthful, but that is a helpful way of stating things, that the vector A has been resolved into its components and written as a sum of its orthogonal projections on the coordinate orthonormal basis vectors. Okay. Furthermore, the numbers AX, AY, AZ, the real numbers, are in fact the Cartesian coordinates of the location of the tip of the vector A. Okay, so I'm just stating these things. I am presuming that these are familiar to you to some extent. If not, please go over this in your spare time a little slowly. Now, we may now use this orthogonal decomposition of a vector in this Cartesian basis to write an expression for the dot product. So if I write A as AX X hat plus A by Y hat plus AZ Z hat, and similarly for B, then when we take the dot product, only 3 terms contribute. The cross terms like X hat dot Y hat will all be 0. So only the 3 diagonal terms contribute. And you find that the dot product is AX BX plus AY BY plus AZ BZ. Okay. So I will leave it to you as an exercise to find the Cartesian components of the cross product of 2 vectors, each of which has been expressed in this basis. Okay, so I will leave that as an exercise to you to find the X, Y, and Z components of A cross B. Okay. Let me now, for now, leave behind this primer on vectors and cross and dot products and go to a little bit about particle position, velocity, etc. Yeah, so this is simply to make a little bit more precise notions that you may already have and which we have even been using freely. So let's talk about the position coordinates and the velocity and acceleration vectors. So I choose my words carefully. I am talking about the position coordinate and the velocity vector. Okay, so notice that distinction. I am not talking about the position vector. Okay, that too is a useful concept which we will talk about in a moment. Now, the instantaneous location of a particle moving in 3-dimensional Euclidean space may be specified by its Cartesian coordinates x of t, y of t, z of t. Okay. So this is the first assertion. If your particle moving in 3-dimensional space and you have already set up an origin and Cartesian axes x, y, z, then the instantaneous location will give you, can be specified using the Cartesian coordinates, which of course depend on time as the particle moves. So as the particle moves, it traces out a curve parametrized by time called its trajectory. So we are mentioning these things with a little bit of care. So this is a parametrized curve. The trajectory is a parametrized curve. And furthermore, it's a directed curve, the direction being that of increasing time. Okay, so I have the obligation then to draw an arrow on that curve and say that t is the parameter along it. Okay. Now, and notice I have used some carefully chosen words, the instantaneous location of a particle. Yeah, use the word location. I am not saying the instantaneous coordinates of the particle. The instantaneous location of a particle referred to a Cartesian system give you the coordinates of the particle. The location is a physical concept. The coordinates are useful mathematical constructs coming from the choice of some coordinate frame. Let me emphasize this once more here. The instantaneous location of a particle is the same no matter which coordinate system we use to describe it. Right? So there is some intrinsic notion of the location of a particle which does not depend on your favorite coordinate system chosen to describe it. All right. So the latter is simply a convenient way of specifying its address. Moreover, the coordinates x, y, and z depend on the choice of origin, I mean, as is obvious, as well as on the orientation of the coordinate axis. If you rotate your coordinate axis, these numbers will change, of course. But the position of the particle or the location of the particle does not change. It is just your way of looking at it that has changed. Yeah, so if we change the origin of our coordinates or the orientation of the axis, we will get a different set of coordinates to describe the location of the particle at a given time. Okay, so all this is at one instant of time. In other words, two people following different coordinate systems will nevertheless meet each other at the common instantaneous location of the particle. So this is what is invariant. Operationally, when I said that the location of the particle is some kind of physical fact, what do I mean by a physical fact? If two people use different coordinate systems to give an address, and they are postman A and postwoman B, and both of them come to that location as per their addressing methods, they will come to the same house to deliver the letter. One moment. Yeah. Okay, so let's continue. So for instance, a courier delivers a letter to the same geographic location, irrespective of whether the address on the envelope says CMI old number 2 2nd Avenue or CMI new number 5 2nd Avenue. All right, so I hope you're able to relate to this. Old numbering system and new numbering system are like two different coordinate systems. And at least in Chennai, we have a generous dose of this. Okay, any question about this?
Yes, sir. So how do you define location without a coordinate system at all? Location has to be...
Yeah. No, okay, it's a good question. Yeah, your point is well taken. So when we say we do need additional objects to define the location of an object at a certain instant, but the point is that there is some concept there that is invariant, and I've tried to convey that through two people meeting at the same location. That notion is the location. So you may not be very satisfied by my answer. So yeah, let me be clear that if you want to say the instantaneous location of my head, you would need to have other reference physical objects. So you might have to say that it is 200 kilometers from some other well-known place in a direction that makes an angle 30 degrees to the instantaneous direction to Jupiter. Yeah. So yeah, to specify the location of the thing of my head, you do need to have other reference physical objects. However, there is some notion of my head being located here independent of what those choice of reference objects are. And that's what I'm trying to convey. I want to use the word location for that intrinsic place, which will be a common meeting point of two postmen. I hope my story is believable.
Yes, sir.
Yeah, the short answer is no. You cannot talk about a location without some reference objects and distances from reference objects, which in effect is some kind of coordinate system, you may feel. Yeah, so yeah, we are dependent on such things.
Yes, thank you, sir.
Yeah, but they need not be some arbitrarily chosen directions. They can be based on physical objects, like the instantaneous location of Jupiter, Sun, and something else. Based on those, you may be able to set it up. Which others can then verify.
So then exactly which term would you say that this thing is invariant? Then what will be the exact blank, the term which to fill in the blanks?
Which thing is invariant?
You cannot say instantaneous location, right? You cannot say that.
No, the instantaneous location of particle is well defined. It is independent of the choice of coordinate system. Okay. Okay, see, well, okay, let us sorry, who was asking this question? Ankan Mukherjee, is it? Is that right? Okay, so you're asking what mathematical quantity is invariant. Is that your question?
Mathematical or scientific, as you say.
Yeah. No, okay. The fill in the blanks challenge question you are given to me is, I would say the position is invariant. Now that I have not defined the position, you may argue, and you are correct. But I think these questions. Yeah, so these questions can be better put into better perspective when one studies the concept of a manifold and vectors and points on a manifold. Yeah, one may have a better understanding that a point of a manifold is an invariantly defined concept, but the coordinates used to describe that point may be different. Okay, so one can try to be a little bit more precise. Okay, so meanwhile, Shyam Patakar asks, will two people using different coordinate system arrive at the same address at the same time? Yeah. No, so your point is very good. They have to be arranged that way. They have to have an objective of reaching a certain address at a certain time. Yeah, that is very important. So yes, they have to have that objective in mind, that the postmaster has told these two postmen, you have to reach this location using your own two different coordinate systems at 10 a.m. today. Without specification of the time, this thing becomes a bit ambiguous. Yeah. So we are going towards the concept of an event, which is a combination of a location and a time. So both of these are needed. Shyam and also our other friend Ankan partly satisfied with this.
Yes.
Okay, fine. So I mean, as far as Shyam's question is concerned, it is not as though the two people will automatically arrive there at the same time. No, they have to make a conscious effort to do so. Otherwise, a postman who takes a tea break will be late and will not arrive at the same event. Okay, so now, so this is a picture of a trajectory and the instantaneous location of the particle. Now I am going to quickly add some things. So the vector, so this is so far I have talked about some sort of God-given things, but for our human use, we will talk about the vector. See, so far I've just talked about the position. Position is a location. It is not a vector, all right? Nevertheless, the vector that points from the origin of your Cartesian coordinate system to the instantaneous position of the particle, yeah, of course, that has some components X, Y, and Z. Yeah, it is called the position vector of the particle relative to that coordinate frame and is denoted R of t. So We have now introduced a vector using a certain coordinate frame. Now, while such a designation is convenient for some purposes, it is important to bear in mind that the location of a particle is not really a vector. I mean, it really is not a vector, all right? The location of a particle is not physically associated to a direction. The location of a particle is not associated to any direction. The location of a particle does not come with any intrinsic notion of an origin. It does not come with any intrinsic notion of a length. Physically, these are not well-defined concepts. If I just say location of a particle. However, for our convenience, sometimes we set up a coordinate frame, we set up an origin, and then erect a vector from that origin to the instantaneous location of the particle. And when we do these auxiliary constructions, then we get a vector which we call the position vector. Okay. So I want to emphasize that the location of a particle is not a vector, but one can construct a position vector for our convenience.
Sir, then what is the location of a particle?
It is some even more basic concept than the position vector.
Sir, I have a question.
I have admitted that I am not able to do better than currently in answering Ryan Hota's question. Not just Ryan, several of you have asked. I have tried to partly answer the question.
I have another question. Sir, you are telling this location and instantaneous location do not matter in respect to coordinates, but in absence of coordinates, this will be absolute only if we have more than one particle. That is, if two particles are there, then in their relative we can measure each other. But what if there is only one particle in an empty space with nothing around it and no coordinate system? Even if it is traveling, how will an observer that is sitting on the particle know that he is traveling?
Okay, I'm sorry. Okay. Two things here. One, our class timing is over, so students are welcome to go to the next class. And now your question was not fully audible to me. I have tried to, from what I can make out, yeah, I have tried to mention that to talk about the coordinates of a particle, or to meaningfully communicate the location of a particle to others, one does need reference objects, one does need reference directions. Yeah, so there is no way of getting away from this. If there is no reference objects of any sort, then you will be very hard pressed to communicate where you are to others. Okay.
Okay.
Yeah. So I mean, if you say there are no reference objects, there are nobody else, then you don't want to communicate with anybody else. So then enjoy your solitude. That's all. Okay, but I think we have to stop here. Any other urgent questions?
Sir, would it be possible for you just to share a list of problems which are not homework problems per se, but just problems so that we can actually work on these concepts? Will that be too much to ask?
Let me see if I can do that. Additional problems just to work out or think about.
Yes, sir.
Yeah?
Yes, sir. Because
Okay.
these concepts are pretty profound, so some of them, and they'll only get more and more dense.
Okay, don't worry, it's not going to become too difficult. No, some of these concepts I have said are actually a bit subtle. There is no doubt about that. And there are people who go through several years of study and are still not clear about these things, or not even aware of these subtleties. So yeah, anyway, I would first encourage you to please go over what we have discussed this morning. That is the first step. If I'm able to suggest some problems, I will do so. I don't promise, but let me see.
Not good reference book for this course.
A good reference book. So I have mentioned a few books. You can see if they have something helpful concerning that. Yeah, I mean, they will all say something or other. Perhaps not in the level of, in the manner we have discussed, but there will be definitely some discussion. I am not, see, I am answering these things based on your questions. It is not from a specific book. Your questions and your seniors' questions and questions from others. It is based on those things. It is not specifically from a book.
Okay, so by the fact that you see that the location of a particle is not really vector, like you mean, okay, so suppose you can see some event happening in front of you, and well, you can choose any coordinate system whatsoever to, but like that the location of the event is fixed in that sense.
Yeah.
Like,
see, okay, look, let's go back to ask what we meant by a vector. First of all, a vector was something, it was a rod-like thing which pointed from some chosen origin to some place. It had a length, it had a direction with respect to your coordinate frame. Okay, so that was what a vector is. Now, position of a particle does not come with any of those concepts. Yeah, I mean,
is it a mathematical concept or like only physical?
No, I would like to say that the position of a particle is a geometrically invariant concept. It's a physical concept. However, to describe it using a coordinate system, we need additional supporting tools. We need some coordinate frame. We need some origin. The location of a particle, I mean, even saying you are in Kolkata today does not say that there is, it doesn't, it's a well-defined concept, right? If I go to Kolkata and search sufficiently, I will find you. But it doesn't say that there is any origin specified. It doesn't say that your location comes with some distance, right? So the concept of a vector, as we have introduced it, and the concept of your location are very distinct concepts. They have very little to do with each other. The position concept can be brought into the framework of a vector only by choosing an origin, a certain orientation of vectors, of frames, and so on. Is that helpful, Aditya Kannan?
Yes.
Sir,
Okay. Yes.
Sir, I do not know how to define manifolds. I only have a basic understanding of them, very basic understanding. But as far as I have seen in metric spaces, they do not define location as such. They define the objects and they define the object's distance from every other object, right? So
okay.
That is, they do not define location, but they define the distance with every other object. It defines a relationship with every other object, not a location as such. So is it the same thing or is it some different kind?
No, I mean, a point on a manifold is roughly what I mean by a location of a particle. These are similar concepts. So yeah. So yeah, perhaps that's right. So you're right. When one talks about a metric space, one can talk about distances between different points, but that point is still there. Yeah.
Yeah. So they define the point, but they do not define the location of the point. Right.
Okay. Okay. For them, that point is simply an element of a set, because that manifold or that space was simply a set of points, and those points were axiomatically God-given objects. They were elements of a set. That's all.
Yes, sir.
Yeah. So if you like that viewpoint, then the locations, possible locations of a particle are simply the elements of some very big set.
Yes.
That is true. That is true.
Okay, sir. Thank you. Thank you.
Yeah. Yeah. Okay. Any other immediate questions? So where may I know where the class recordings are available? The class recordings are, the link to the class recordings are available on the course website. So I hope you can, they are updated every so often. So if you go to that course website, you will get a YouTube link, which will take you there. Okay, any other questions? If not, we shall end this meeting and meet tomorrow again at 10:30 a.m. So have a good afternoon.
So tomorrow we have a compensatory class at 10:30.
Indeed, we are compensating for Tuesday's missed class at 10:30 a.m. tomorrow. So please be present.
Will it be the same link or will you send us a new one?
Same link for all classes. Unless there is any change, it is the same link, same Zoom link.
Yes, sir. Thank you, sir.
Thank you. Yeah.